Physics 2211 Lab 3 Black Holes and Orbits. Hello, my name is Julian, and this video presents my analysis and results for Lab 3 Black Holes and Orbits. The purpose of this lab was to use computational modeling and Newtonian gravity to analyze orbital motion in two different situations. In part 1, I used position data of a star orbiting a black hole to estimate the mass of the black hole. In part 2, I simulated the motion of a spaceship near a planet-moon system and determined an initial velocity that allowed the spaceship to orbit both bodies without crashing. Using the trajectory data and Newton's laws, I found that the mass of the black hole was approximately 2.77 times 10 to the 50 kilograms, and the initial velocity needed for the spaceship to orbit both the moon and planet was approximately 9.57 times 10 to the 4th meters per second. Models of physics principles. This lab relies on two main physics principles, Newton's second law and Newton's law of universal gravitation. Newton's second law states that net force acting on an object is equal to the rate of change of its momentum. Momentum is defined as mass times velocity. In equation form, this means the net force equals the change in momentum divided by the change in time. The gravitational force between two objects depends on their mass and distance between them, following Newton's law of universal gravitation. These equations allow the computational model to determine the forces acting on objects and update their motion over time. Part 1. Determining the black hole mass. Part 1, I analyzed the position data for a star orbiting a black hole located at the origin. The system I consider as a star, while the black hole acting as an external source of gravitational force. The initial condition included the star's mass, which is 2.2 times 10 to the 30 kilograms, and the interval, which was 1 day or 86,400 seconds. First, I calculated the star's velocity from change in position between the data points. From the velocity, I calculated the star's momentum. Then I calculated the change in momentum between the time steps. Dividing this by the time interval gives the rate of change of momentum, which, according to Newton's second law, is equal to net force acting on the star. Using the magnitude of net force and the star's distance from the hole, I rearranged the gravitational force equation to solve for the mass of the black hole. This calculation was read from many points in the orbit, producing many estimates of the mass, and I averaged these values to obtain the final result. The estimated black hole is approximately 9.57 times 10 to the 33 kilograms. What does this mean? Net force for the rate of change of momentum. Although Newton's second law tells us that the net force equals the rate of change of momentum, these concepts represent different physical ideas. The rate of change of momentum describes how the motion of an object changes over time, being determined directly from measurements of position and velocity. The net force, on the other hand, represents the physical interaction because causing those changes in motion, such as gravitational attraction. In the simulation, the rate of change of momentum was calculated from the observed motion of a star, while the net force was interpreted as the gravitational force from the black hole. The parallel component of the net force changes the magnitude of the momentum, meaning it speeds up or slows down the star. The perpendicular component changes the direction of the momentum, causing the star to follow a curved orbit. Part 2. The spaceship orbiting simulation. Part 2, I simulated a system containing a planet, moon, and spaceship. The planet was fixed at the origin. The moon initial orbit the planet. Spaceship started slightly above moon surface. The computational model calculated gravitational force between the moon and the planet, the spaceship and the moon, and the spaceship and the planet. Newton's second law that was then used to update the velocity and position of the moon and spaceship at each time step. By adjusting the initial velocity of the spaceship, found a trajectory where the spaceship was influenced by both the moon and the planet and orbiting through a complex path without crashing. The initial velocity that produced this orbit was approximately 9.57 times 10 to the 4th meters per second. What if modeling the entire system? In order to model the entire system realistically, we need to include gravitational interactions between all objects: the black hole, the star, the planet, moon, and the spaceship. However, some interactions would dominate. The black hole would exert the strongest force on the star because of its enormous mass. Similarly, the planet would dominate the moon's motion. Smaller bodies like the spaceship would be influenced by both the planet and the moon, but their gravitational effect on larger bodies would be relatively small. A complete model would calculate every gravitational interaction at the same time step, which is known as an n-body simulation. For conclusion, in summary, this lab uses computational modeling and physics, Newtonian physics to analyze gravitational motion. By analyzing the motion of a star orbiting a black hole, I estimated the black hole mass to be 2.77 times 10 to the 50 kilograms. In a second simulation, I determined an inertial velocity that allowed the spaceship to orbit both the moon and a planet without crashing. These results demonstrate how Newton's laws in gravitational motion can be used to predict complex orbital motion in astrophysical systems. Thank you for watching.